I mean, I have two pencil sharpeners. I don't think either one works very well. But. Try the one in the back. Okay. So the lesson today, we jump to chapter 2. It's 2 different sections. Using integers and rational numbers, adding real numbers. That's good, isn't it? And these are definitely in support of an SOL. You can see when our quiz is today. We're going to have another quiz before the test. There's way too much time in between now and the test. And the test should be for us on the 28th. It's like a week from Monday. Okay. So first we got to discuss real numbers and subsets of real numbers.
Should I draw them?
Whatever helps you out.
Yes.
Okay. Again, I'll tell you, learn to take notes that are meaningful to you. Understand that a graphic like that probably just came from the book. You know, so you actually have this. So understand you've dealt with Venn diagrams before, have you?
Yes.
You're probably starting about kindergarten or something like that. So what does it mean to have this circle of whole numbers inside this rounded rectangle of integers? What does that mean? Well, we're not really talking about what they are. We're just saying, what does it mean when you put one shape all the way inside another shape? Yeah, it means that all whole numbers are integers because that circle is completely inside the shape which represents integers, right? And all integers are rational numbers for the same reason. Is it true to say that all integers are whole numbers?
No.
Does it go backwards?
No.
No, it doesn't go backwards, right? It only goes because the whole numbers is inside the shape. They have to be integers. But all that lighter blue area here, right, that could be integers that actually don't fall in the set of whole numbers. There's actually one more set of numbers that we usually start with.
Irrational.
No. What is it? Natural numbers, right? And natural numbers are kind of like the whole numbers. It just, what's the one difference between natural and whole numbers? The zero, right? So here on a number line, you could see that the natural numbers start at 1. They're also known as the counting numbers, right? Because you start counting at 1. 1, 2, 3, 4, 5, 6, to infinity, right? Positive numbers. But if you add the 0, those are the whole numbers. And the integers are plus and minus whole numbers. So you can see it goes 0, 1, 2, 3 to positive infinity, 0, negative 1, negative 2, negative 3 to negative infinity. Where would rational numbers fit into that number line? Since we already said whole numbers are rational numbers. Whole numbers or integers are rational numbers. Yeah, in between all of these whole numbers are fractions and decimals, right? Those are rational numbers. It's also true that all of the numbers you see there, they're all rational numbers too. And we'll talk about that in a minute, why they are. But in the in-between of those numbers, there's rational fractions and decimals that are rational numbers. The thing you need to understand, you need to keep in mind, because I know that you will take SAT tests and things like that, the words rational and integer are used, not like it's a specific math thing to know, but just like it's something we all ought to know about English, that a rational, but they say find a rational number or something like that. They're not, the point of it isn't to quiz you what's a rational number. They just expect you to know what it means, right? Or an integer. But they're not that uncommon of words that we just expected to know what they mean. And I can tell you, having taught classes way higher than this, that we still struggle all the time with what's rational mean. Okay, let's see. So we start out by saying we're going to graph some integers on a number line and then tell which number is greater. And I did for two of them here. Right? I'm going to do for -3 and -4, and then I'm going to do for 3 and 4. That's not very good, but I can't do this, it's so small. I'll forget it. So here we go, black. So I'm going to put on enough tick marks. Right. So if this is 0, 1, 2, 3, 4. -1, -2, -3, -4. Where do you find the -3 and the -4? Yeah, here's the -4. Here's the -4. Why is that doing that? And there's the -3. Now here's the thing that we really got to be getting out of this. It comes up. Which is bigger? -3. Whatever is to the right on the number line is bigger than whatever's on the left. Right? How about 3 and 4? Let me go 0, 1, 2, 3, 4. So here's the 3 and here's the 4. And so which is greater? 4 is greater because it's to the right of 3. You know, this comes up, the fact that the order of the numbers is reversed when you get the other side of 0, and sometimes it causes confusion. But if you ever just think of it in terms of the number line, it helps you to keep it straight. Right? That was not a good graph. So try to do this. Graph three number lines, plot these points, and tell which one is greater. You know, besides the just plotting these points, saying which one is greater, make sure that when you make tick marks on a number line or when we're doing it in a graph for x and y, like I was showing before, that you make them equally spaced. Right? Try to have a little consistency in the way you space things, because sometimes it can give you a false representation of what you're looking at if they're not. Right? So it helps to be careful about that. So if I'm going from 0 to 4, I'm going to go 0, 1, 2, 3, and 4. Right? And the 2 points, I'm just going to put them here in black. 0 and 4. Which one is greater?
The 4.
The 4. Okay, 2 and -5. Okay, if I'm going to put now that's going to be 7 numbers, actually 8 tick marks. I need to space them closer together. -5, -4, -3, -2, -1, 0, 1, and 2. So I'll put the 2 and I'll put a 0 just to keep us grounded. And that should be -5. 1, 2, 3, 4, 5. Right, there's a -5. There's the 2. Which one is greater?
Oh, the 2.
Dos. Right, and then we go -1 to -6. So I need 6 marks. 1, 2, 3, 4, 5, 6.
Please pardon the interruption. Any students holding an SOL testing pass, please report to your testing location at this time. Thank you.
Okay, and which one is greater?
-1.
The -1. Okay, whatever's to the right. Even though, 6 is bigger than 1. -1 is bigger than -6. Because of where they fall in the number line. Now, rational numbers are any number that can be written as a fraction. It doesn't have to be written as a fraction. Like natural numbers are 1, 2, 3. Right? How could you make that a fraction? Just put it over 1, right? There you go. that makes it a rational number. If you can write it as a fraction, then it is a rational number. Okay, whole numbers the same way. Obviously, fractions are fractions. But even when it comes to decimals, if you're looking at something like 0.6, I mean, we can tell that's going to be a fraction because that's the 6 is in the tenths place, right? That's actually equal to 6 tenths. Yeah.
So, all numbers are just like 0 to whatever, and then integers to either negative, other than negative.
Yeah, the integers are also negative. I probably should have had those in the list too. So natural numbers, whole numbers, integers, all of those you just put over 1 and you've got a fraction. Decimals also. If they terminate, then you're going to be able to do this kind of thing, right? Just put it over the right thing. What would be the fraction if I had 0.123? What's the fraction? 123 over 1,000, right? That 3 is, it's tenths, hundredths, thousandths, so it's 123 over 1,000. So even though it's written as a decimal, it can be written as a fraction. Now the one that may not seem like it is a rational number would be a decimal that doesn't terminate, something like 0.3. How do you write that it repeats itself? Usually you put a bar above it, right? That means just keep repeating the 3. But any number that has a repeating pattern to it can also be turned into a fraction. I mean, this one in particular, I think we probably already know that's 1/3. But even if I had something like, 0.23 repeating, I can turn that into a fraction. And if you're interested to see, this is how you would do it. If let's say I set x equal to 0.23 repeating. What's the effect of multiplying times 100? When you multiply times 100, what does it do to the decimal point? It moves it to the right, or actually to the right 2 places. So that's if 0.23 repeating is the x, 100x is going to be 23.23 repeating. Now what happens if I subtract 23.23 repeating minus 0.23 repeating? You're just going to get the 23. The repeating part drops out. And on the other side, and this is a little advanced for us, but that's going to be 99x equals 23. So that's the process you go by to show that a repeating decimal also is a fraction, right? So what's the only kind of decimal that is not a rational number? A non-repeating, non-terminating decimal, right? And the perfect example of that is pi. That's the one we always use, pi. 3.14156 ... goes on forever. Yeah. Okay, sorry. Let's see. So here's an example. Tell whether each number in this list is a whole number, an integer, or a rational number. And then order the numbers from least to greatest. This is my example to do for you. Okay, so 3. Is 3 whole,
Yeah.
integer, or rational? It's actually whole, integer, and rational, right? Because if it's in one, it's in all 3, right? If it's in whole, that's is inside the other shape. So, but we'll just say it with the interior shape that it represents. So we'll say this is whole. What about negative 1.2? I mean, that's a decimal. Could be represented as a fraction, so that'll be rational. What about negative 2? That would be integer. And what about 0? 0 is a whole number, right? So, okay, now put them in order from least to greatest. Which is the smallest?
Negative 2.
Negative 1.2. And 3. How about the next one? 4.5 is rational. Negative 3/4. Negative 2.1. 0.5. Okay, put them in order from least to greatest. Which is the smallest of those? Negative 2.1. Which is next? Right? Negative 3/4. And then 0.5, and then 4.5. So if you're ever confused about that, right, you just have to think like, which two integer values do these numbers fall in between? I mean, if you're not, negative 3/4, in between which two integers does that fall? Right, it's negative, right? So the question would be, is it between negative 2 and negative 1, or negative 1 and 0? So 3/4, positive 3/4 would be between 0 and 1. Negative 3/4 would be exactly the opposite. And where would be the negative 2.1? Would that be between negative 2 and negative 1, or negative 3 and negative 2? Negative 3 and negative 2, right? You're going away from 0, right? So negative 1, negative 2, and it's at about 1/10 of the way towards negative 3. So you try that. Say what sets they're in, the most interior of those, and then put them in order. What kind of numbers were in the number 6? What are all those? They're all rational numbers, right? In fact, on the next group, what are they? There's one of them was a whole. Okay, put them in order. Which is the greatest of the first four? There's only one positive number, right? So it has to be the biggest, 3.6. And the only question now is what's the order of the others? The smallest is negative 2.8. The next is negative 1.5. The next is negative 0.31. How about this? The least of them is, there's only one negative, so it has to be that. What is it? 2/3. Then? Nope. 0. Right? And then what? 1/6 and 1.75. Now, if you really are comparing these numbers, it's kind of nice if they all look like decimals, then it'd be more easy. But I mean, 1/6 you should recognize as a number that's less than 1. So definitely you could order it with the 1.75 correctly. So we have to define the word opposite, at least mathematically. You probably already think you know what an opposite is, right? In math, positive and negative numbers that are the same distance from 0 on the number line are called opposites. So 4 and negative 4 are opposites. And notice the way that that graphic is drawn, that it's got the point at negative 4, it's got a point at 4, and it's also showing you the distance from 0 for both of those. And what is the distance from negative 4 to 0? Positive 4. And the distance from 0 to 4? Positive 4. So the distance from 0 is always positive. Okay. Are there any other pairs of opposites on that graph? Opposites. Does 0 have an opposite?
No.
Not really. Is 0 positive or negative? It's neither. It's not considered to be either positive or negative. It's in the middle. But in any case, we know what it means to be opposite. Now, it seems like a silly concept in a way, but we're going to use it now to define another concept which is not a silly concept, which is called absolute value. right? The absolute value of a number is the number's distance from 0 on the number line. So like if I go back to that same graph, what was the distance from -4 to 0? +4. And what was the distance from +4 to 0? 4. In either case, it was 4. Right? So the symbols that we use to represent absolute value are straight brackets. Right? That's what these things are on either side of these numbers. Those are absolute value brackets. Right? The absolute value of -4 is 4. The absolute value of +4 is 4. So what does it look like absolute value symbols do to a number? It makes them positive, right? What's the effect of taking the absolute value of a positive number? No change, right? It stays the same. What's the effect of taking the absolute value of a negative number? It flips it to positive, right? So the output of an absolute value is always positive. Yeah. Right. If there was a minus in front of it, that would change things, right? But we're just talking about what's inside for now. Let's see. So example, if A is -2/3, then the absolute value of A is 2/3. They've got a lot of stuff in the middle there. But my guess is that you would just say, look, the absolute value, you'd probably jump right to the +2/3. Right? Take the negative, make it positive. How about if A is 3.2? Then the absolute value is 3.2. Doesn't change a positive number, but it does change a negative to positive. So you try, of course, these. Find absolute values. And I won't even pause the recording. So make sure we use those symbols, right? You don't want that to be the first thing that's confusing you in the homework, is that you don't know those symbols. Right? What's the absolute value of +5.3? 5.3. And the absolute value of -7? +7. And the absolute value of -4/9? 4/9. Right? Simple. Okay, now we jump to the next section, which is called adding real numbers. Right? Adding real numbers, the first thing you do is you plot the first number, and the second thing is you go left or right from the first number on a number line, depending on whether it's the second number is positive or negative, or if you're adding or subtracting. So you can see again, we know that on the number line, greater than is always to the right, less than is always to the left. So they do this in 2 steps, and some of it probably is trivial, right? But we're still going to go through it, and we still make mistakes with adding and subtracting numbers, especially when there's a mix of signs. So maybe this helps people that are, having to deal with that kind of thing. So an example would be -3 plus 6. So the starting point is -3. Plus 6 means you should go to the right, 6. So start at the -3 and count. 1, 2, 3, 4, 5, 6. The answer is 3, right? So that equals 3. So in your mind, you just kind of picture, you started -3, which was to the left of 0. When you added 6, the first 3 just got you back to 0, and then how much was left? 3, right? How about -4 plus -5? Start at -4, and saying plus a negative means go which direction? Left, right? So you're going to go 1, 2, 3, 4, 5, right? So when these now, they both had the same sign. So when I add a negative number to a negative number, you get an even I shouldn't even say the absolute value is bigger. The number is not bigger, right? But it's more negative. You're moving even farther to the left when you add two negative numbers. So this one would be -9. What if you add two positive numbers? It's going to be more positive, right? It's going to move farther to the right on the number line. So go ahead and try this one. I mean, we're doing this kind of in two different ways. Once we'll do it with the number line, then we use absolute value. Got blue. So first I start at the 7, right? 1, 2, 3, 4, 5, 6, 7 would have been right there. There's 7. And the -2 means go which direction?
To the left.
Right. So then we're going back 2. Right? That's the -2. And so where do we arrive? 5 equals 5 equals 5. Eight plus -11. So let's see, 2, 4, 6, 8. Now, because one's positive and one's negative, the -11, right? When I go, it's going to take me 8 to get back to 0. And then how many are left over? 3, right? So I'm going to get to -3. So I go, here's 8, right? And then here's an extra 3, -1, -2, -3. So in total, that's our answer. How about -8 plus 4? The starting point is -8, which is here, and now we're going +4, which means we're going which direction? To the right, all right? We're going back 4. 1, 2, 3, 4. And the answer is -4. And the last one, -1 plus -4. Starting point, -1. Okay, and then we're going to go how many to which direction? So we start here, and we're going to go left 4. The answer is -5. That's using a number line. Like I said, I don't think you're usually going to be pulling out a number line to do these things, but it can help, sometimes just to try to picture what's going on. The sum of two positive numbers is positive and greater than either addend. Okay, what's an addend? The things you're adding together, right? It's another math term. We don't use it a lot, but it's there. The sum of two negative numbers is negative, and its absolute value is greater than the absolute values of either addend, right? It's getting further to the left. If the sum of a positive and a negative could be positive, could be negative, and it just depends on which has the greater absolute value, right? That's going to determine it. So these are examples, finding the sums using absolute values. This is using the rules that the book has, which you may or may not do this exactly. That's okay. But you see what they're saying is, because you're adding two negative numbers, add the absolute values and then put a minus in front of it. Right? They added 5.3 and 4.9, and then they put the minus in front. The second one was 19.3 plus -12.2. So one's positive and one's negative. They're saying subtract the greater absolute value minus the lesser absolute value, and then put the sign of the greater of the two. So 19 minus 12.2, and because 19.3 was bigger than -12, the absolute value, then it's positive. If it had been a -19.3 plus 12.2, you would have still done 19.3 minus 12.2. But because the bigger absolute value was the negative number, you put a negative in front of it. Yeah, I agree that some of these, I don't think this way, It is the way it's presented. Try these. Try these. Oh, so the first one, they're both negative. So how do you add them up?
You add the negative.
And
You just add the.
then what?
You put the
And put a
negative.
negative on it, right? I mean, when you're adding them, you're not really dealing with the negatives. So you just say, I'll add them up, and then I put a negative on at the end. So this is 0.6 and 6.7, which is 13, 7.3. But because they were both negative, it's negative. Okay, now the next one, it's a positive and a negative. So we know that we should be subtracting the larger minus the smaller absolute values. Right? We should definitely be doing 16.2 minus 10.1. 2 minus 1. 6 minus 0. That was a 10. And because the bigger absolute value was actually the 16.2, right, that means it's negative 6.1. And how about on the last one? Same deal, right? It would have been nice if they gave us one that was actually the opposite, but they didn't, right? So negative 13.1, positive 8.7, subtract the bigger minus the smaller, and then keep the sign of the bigger. 11 minus 7, 4. Okay, we had to borrow there. 12 minus 8, 4. And because the negative 13.1 absolute value is bigger than the 8.7, it's minus. Easy? Okay. So then we get into what are called the properties, right? And these properties, we're calling them properties of addition. They're really properties of real numbers. And you're expected to know these. I don't know what level of that they are included in your SOLs. I know they're included some in the Algebra 2 SOLs, and there are probably some in yours too. But the first one, commutative property, just means order doesn't matter when you're adding two numbers. 2 plus 3 equals 3 plus 2. Or they have an example, 3 plus negative 2 equals negative 2 plus 3. And sometimes it serves your purpose to switch the order, helps you do computations. You can do it and be confident you're not changing the answer. Associative, what's changing when we look at this this formula? The parentheses, right? It doesn't matter the grouping. You know, if I can group the first two or I can group the last two. And we know order of operations wise what that means, right? Because we would go to the grouping symbols first. But it won't make a difference to the final answer, not for addition. Okay. You know, there's their example, negative 3 plus 2 plus 1, but the negative 3 plus 2 is in parentheses, so we would do that first. The next, on the right-hand side, it's negative 3 plus 2 plus 1, right? And that side, we would have to do the 2 plus 1 first. In either case, what's the answer? Yeah, what are they equal to? Negative 3 plus 3. 0. Right? This one is negative 1 plus 1, 0. So it doesn't matter if the grouping symbols. The identity property for addition is if you add 0 to a number, it doesn't change the number. You get the identical number back again. In fact, you call 0 the identity element for addition. Right? 0 is the identity element for addition. So negative 5 plus 0 equals negative 5. And then the inverse property is, what number do you add to a number to get back to 0? Right? They have an example, negative 6 plus 6 equals 0. Right? So you would say that that's the additive inverse property. But what are those two numbers? Those are opposites, basically. When we defined opposites, we did this. So, you know, there's the general thing. A plus negative A. If you add two opposites, you get 0. That's called the additive inverse. So now, I kept the properties up there so we could just see how that works here. But you notice the first one was an example of Associative, they move the parentheses, right? The second one was an example of, they added opposites to get 0, so that's inverse. And the third one was an example of, right? So you try to identify the properties here. Here, just write down the property. What was the first one? That looked like an inverse property, right? How about the second one? Identity. What about the third one? Commutative. Okay. Okay, what's this one? I'm going to write a new one up here. You tell me what's the property. Incorrect. Yeah, I didn't. What did I change there? I switched the order of what was being added, but actually I didn't change what was in the parentheses. It's still 1 plus 2. But that is a typical kind of problem that's kind of designed to trip you up, right? So I'm just giving you an advanced warning. Yeah. There is a property like that when we get to multiplication. The 0 property of multiplication, right, which is a very important property when we get to it. So that's what we did. That's the homework.